Okay, it's already 6:10. We should start now. Uh, is my screen visible and am I audible?
Yes,
Good. Okay. So today in live session 3, we'll discussing regarding different kinds of material strengthening mechanisms. What we have gone through in earlier week. So kind of what are the different mechanisms like. There can be grain size reduction, there can be solid solution alloying, there can be cold working, strain hardening. Again, we'll do some theoretical, again, brush up the theoretical concepts, and also we'll do some numericals as usual. So let us start then. Uh, in question one, it says that Hall pitch relation describes relationship between materials stiffness and grain size, or hardness and grain size, or UTS and grain size, or yield strength and grain size. So
yield strength and grain size.
right. So if you see the Hall pitch relation, it gives you the relation between yield strength and grain size. Now in terms of strengthening, if you see, uh, it's kind of the ability of a metal to deform plastically, and it depends on what, it depends on basically the ability of dislocations to move, right? So if you see strengthening mechanism, so somehow it is based on this ability of dislocations to move, right? Now this hardness and strength are related to how easily a metal plastically deforms. So by reducing this dislocation movement, and mechanical strength can be improved, right? And to the contrary, if dislocation movement is very easy, or it is kind of unhindered, the metal will be soft and easy to deform, right? Now what are different kinds of strengthening mechanism you have come across? So there are different kinds of strengthening mechanism, right? So there can be this grain size reduction, then there can be solid solution alloying, you can say. Then there can be strain hardening or cold working, and finally there can be kind of heat treatment, right? So annealing or heat treatment. Now, in terms of these dislocations, what are different kinds of dislocations you have come across? Means why dislocations happens? Because there will be atomic defects, right? So in terms of dislocation, there can be. Can you say the names of what kinds of dislocations are there for imperfections in solids?
Edge dislocation and groove dislocation.
Right. So there can be edge dislocation, or else there can be screw dislocation. No. Now, if you see in edge dislocation, it's basically kind of a extra half plane of atoms is inserting in a crystal structure. That's where the defect is there, right? So if you have this kind of structure, like this, now this is your extra half plane. right? So this is kind of edge dislocation. And if you see screw dislocation, in screw dislocation, it is like you can say it kind of spiral planar ramp resulting from shear deformation. So there can be some kind of orientation over there. है ना? If I try to draw the 3D diagram of screw dislocation, uh, let me draw some schematic. So it may look like this. So this kind of so this may not be that much clear, but yeah. So in terms of screw dislocation, you can think of some spiral planar ramp resulting from shear deformation. Now, these dislocation motions are reversible or irreversible? Any idea? So, whenever these dislocations are moving, you are having plastic deformation, right? So, these are irreversible in nature. So, dislocation motion always leads to plastic irreversible deformation. है ना? And anything I'm missing? Yeah. So, in terms of this Hall pitch relation, if we try to figure out what happens in Hall pitch relation, so in Hall pitch relation, it is like, what is the relation? So this sigma y equal to sigma, what happened? Yeah. So sigma y equal to sigma naught plus k into d to the power minus up. Now what is sigma y? This is your yield strength of the material, right? Yield strength of material. Then sigma naught is base metal yield strength, and d is what? Grain dia. Now, if you think of these grain boundaries are kind of it you can think it of some barriers to sleep to happen, right? So sleep to happens means dislocation motion. It is kind of barriers to dislocation motion. So whenever this is acting as a barrier, the strength increases with increasing this angle of misorientation. So angle in the sense, if you again let me draw something. Let us say this is your atomic arrangement. Now let's say this is your extra hub plane, and here is your slip plane, and then you have the grain boundaries like this. So there will be orientation mismatch over across the grain boundary. Now whenever increase the you increase the grain boundaries, that means you are reducing the grain size. That means your dislocation motions are You are providing more barriers to the dislocation motion, and you are somehow enhancing the strength, right? So this concept is clear, correct?
Yes, sir.
Great. So we'll move to the next question. So in question two, it says strengthening mechanism in metals mainly relies on strategies two. There are four options. One is reduce the number of dislocations in the microstructure, eliminate the formation of high angle grain boundaries, prevent the movement of dislocations in the microstructure, and improve the purity of the metal.
Movement of dislocations.
The third option, right?
Yes, yes, sir.
So whenever you are preventing the movement of the dislocations in the microstructure, you are somehow strengthening the metal. So that's what we discussed in our earlier question. The same thing. Now in question three, it says how solid solution strengthening happens. So solid solution strengthening mechanism involves reducing the grain size in the metal, or subjecting the metal to plastic deformation, or melting the metal and resolidify via quenching, or preventing slips in the microstructure through distortion of lattice strengths. So what happened in solid solution strengthening?
Fourth option.
Right. So basically, if you see in solid solution strengthening, in case of solid solutions, the stress fields around the solute atoms interact with this stress field of a moving dislocation. No? And thus, these offer a greater resistance to dislocation motion than the pure crystals. So in solid, so this solid solution strengthening, there are two different things. One is size difference between solute and solvent atom, and then there is concentration. So then there is concentration of solute atom. Now this basically, in addition to the size difference, intensity of the stress field around the solute atom also dependent on this elastic modulus of the solute. है ना? Now if we try to draw some figure in terms of solid solution strengthening, uh, let us take this figure. Let us take this figure. Now basically what happens is impurity atoms distort the lattice and generate the lattice strengths. So what happens is there will always be some kind of impurity atoms, है ना? So you have come across this substitutional solid solution, interstitial solid solution. So there are two different things, substitutional and interstitial. Now whenever there will be these impurity atoms, they always distort this lattice and generate lattice strengths. Now, can you tell me this at this region what kind of stress will act? Will it be compression or tension? So there is this extra half plane acting over here.
compression.
So whenever this extra half plane will be there, these will try to push these atoms like this, and for that reason the subsidiary regions will feel some compressive stress over there. So the complete region will feel the compressive strain over here, and the vice versa will be here, you know. Means if you think of in terms of some in terms of atoms. So let us say you have this kind of atomic arrangement. uh, Say you have this kind of atomic arrangement, and then you have these smaller atoms over here. Okay, so smaller atoms over here like this. So whenever you have these smaller atoms over here, all these regions will feel compressive lattice strain. Correct? And then of course, if you will have this let's say you have this bigger atoms over here. So whenever there will be bigger atoms over here, this bigger atom will try to push the things up, है ना? So here it will feel tensile, right? So that's how these impurity atoms like substitutional or interstitial, whatever, these acts as a barrier in for your dislocation motion. Correct? Understood?
Yes, sir.
Okay. So we'll move to the question 4. This is a numerical question, and yeah, this is based on this stress strain curve. Initially, you try, then we'll discuss. Let us take 5 minutes. So you have these K, N, and M values for a material which is SS. So those are given values for K, N, and M. And then you have a test piece of some initial width, thickness, and length which are given. And you have to determine the increase in load when extension is 10% and extension rate of gauge length change from some given value to some another given value, which is zero point 0.5 to 50 per minute. So you need to find out the increase in load. So this we need to find it out, right? Now, can we in terms of this stress, strain, and strain rate relationship, we are aware of this equation. है ना? So n is strain hardening coefficient, not strain hardening coefficient. What is n? And m is strain rate. Now, if you have this equation, then you have this kn and m values for SS 1140.35 and 0.01. How should we proceed? This was not sensitivity, this is exponent actually. So, any idea how should we proceed? You have this k, n, and m values for SS sheet, and then you have this initial width, thickness, and length. Those are also given, and then we need to determine the increase in load. So, let us start from here itself. We need to find out delta F, right? The increase in load. So this will be F1 minus F2, the initial one and the final one, right? So this is, let's say, area is constant and this is sigma 1 minus sigma 2. Now, from volume constancy, what we can say? Area into length is equal to original area into original length, right? Now, you
Yes.
can find out the area from here, A naught L naught by L, right? So you have this A naught as 12.5 into 0.45. This is your A naught, that into 50 divided by what will be L. So you have this extension as 10% extension. So 50 plus 50 by 10. So this is 55, correct? So how much A is coming? So A is basically the, you can think it of instantaneous area or the final area. So how much A is coming?
5.11.
So this is coming as 5.1136. This is an mm square, right?
Yes.
Up to this understood how we are getting this A value.
Yes.
Now, uh, now what we need to find out? We need to find out this epsilon value, and strain rate value is changing from zero point 0.5 to 50 mm per minute, correct? Now, how can you find out this strain value? So if you think of some true strain value, this is basically log L by L naught. So L is your original length and L is your final length. So how much is coming this? Log, this was 55 by 50.
0.0953.
It's a 0.09. Okay.
Yes.
Now, if you have find out this epsilon value, and then these two values of strain rates are given. So one is epsilon 1 dot, which is point. Let's say this is V by L, and a strain rate is V by L, which is coming as zero point 0.5 by 60. This zero point 0.5 mm per minute. So we are converting into mm per second. That divided by 50, correct? And epsilon 2 dot is, so 50 by 60, that divided by 55, correct? So what are these values? Epsilon 1 dot and epsilon 2 dot.
Silent 1 dot is 1.67 into 10 raised to minus 4.
Mm-hmm. This is in terms of per second. And epsilon 2 dot.
0.015.
Great. So you have this epsilon 1 dot epsilon 2 dot value. You have this epsilon value also. So there is change in strain rate actually. है ना? Now from here, what will be the sigma 1 value then? So sigma 1 will be k into epsilon to the power n, epsilon 1 dot to the power m, correct? And sigma 2 will be k into epsilon to the power n, epsilon 2 dot to the power m, right? And n and m values are known, n, m, and k. All three are known. So can you give me the values for sigma 1 and sigma 2? How much this is coming in megapascal? So basically in terms of Newton per mm square. Okay, anyhow, you got the concept, right? So you can find out the sigma 1 and sigma 2 value from here. And
Yes,
once you get
silent
the,
value will be same in both the cases.
sorry,
Strain value will be same in both cases.
yeah, we are taking strain value as same. So there is change in only this strain rate value. So there is this extension rate is changing from zero point 0.5 to 50 mm per minute.
But initially there will be no strain when it starts to pull up when you apply the load initially.
Yes, means from physical point of view, initially it will not. There means maybe there is some mistake in plotting the numerical. Uh, Before pulling out, there will not be any kind of strain. Yes, you are right. And after pulling out, it is coming. This extension is coming as 10%. No, 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 no. The thing is, the thing is, we are misunderstanding actually. So the thing is, you have this extension. You have this extension as 10%. Okay, you have this extension as 10%. So the numerical is saying this. Whenever you are having this extension as 10%, the first case is you are doing the extension in terms of 0.5 mm per minute. This is the rate of extension. And the second case is 50 mm per minute. So for the second case, this is the rate of extension. The extension is same for both the cases. Are you getting
Yes,
it?
these are two different cases.
Sorry.
There are two different cases, right?
Yeah, there are two different cases. We are extending it up to 10%. So the strain is same for both the cases. We have extended from 50 mm to 55 mm, but the rate of extension we have changed. One is fast, one is slow process.
Okay, understood.
So epsilon dot, the strain rate value we are changing. That's why we keep the strain value as constant.
Yes, I got it.
है ना? So once you get the sigma 1 and sigma 2 value, you will get the force value also by multiplying it with area. And then you can get the increase in load. Right?
Yes.
Any confusion?
So area will be the final area.
Area will be the final area. Exactly. Area will be the final area. Okay, let me write it. Area will be the final area. Should I move? Or else you can finish. You can finish the numerical.
Increase in load is 105.85 Newton.
Oh, what is this value? Delta H?
105 point, yeah, delta
105,
105.85.
105.85, correct?
Yes, yes,
Okay, let's assume that this is correct. Anyhow, you got the idea, right?
yes, yes,
Right. So this is also from stress strain curve. So here you have this true strain to strain diagram of a strain handling material, which is shown in figure. And then you have provided this. First, there is loading up to point A. First, there is loading up to point A. That is up to stress, which is given 500 megapascal, and then strain is also provided. So for this point A, stress is 500 megapascal and strain is zero point 0.5. Then from point A, there is unloading up to point B, unloading up to point B, that is trace of 100 megapascal. So here at point B, trace is provided as 100 megapascal, and given that Young's modulus E is equal to 200 GPa. Now what will be the epsilon B? This is very simple actually. So what can you tell from basically value of E? Can you tell that this is the slope of this line, slope of line
yes,
AB
yes,
in elastic region? है ना?
yes,
So if this is your slope E, so E is basically, you can think it of this tan theta value, correct? So this is coming as AC by BC, right? So if E is provided as 200 GPa, which is 200 into 10 cube megapascal, that will be equal to, what is AC? AC is basically this difference, 500 minus 100, correct? That
yes,
divided by this BC value. So how much BC is coming? 200 into 10 to the minus 3. So 0.002, right? So if BC you have got, what will be epsilon B? You have this total strain as zero point 0.5, that minus 0.002. How much is this?
0.5 498.
Is my screen visible, right?
Yes.
You got the concept of this question?
Yes.
Great. So, I'll move to the next question then. So, here, yeah, here it is saying that you have these previously undeformed specimens of some same metals. So, the material is similar for two cases, which need to be plastically deformed by reducing their cross sectional areas. One has a circular cross section and the other is rectangular. So one you are having as circular and the other is having as rectangular. Now during deformation, the circular cross section has to remain circular and then rectangular has to remain rectangular. And then you have it is provided that their original and deformed dimensions are provided. So for circular, initial dia is 15.2. For rectangular, initial area is 125 into 175. So this is the length and width. And for deformed dimensions, the dia and the areas are provided. So you need to find out which of these specimens will be the hardest after deformation. So how can you tell that which material is harder?
By the reduction in area. More
Correct,
the
correct.
reduction in area, more harder.
So basically, you can find out this percentage of reduction in area. है ना? So original minus the deformed that divided by the original. Correct? So the one which will have the higher percentage that will be harder, right? So when I start calculating, so for circular geometry, you have this pi r naught square minus pi r t. D is basically deformed dimension that divided by pi r naught square that into 100%. So let us first calculate for the circular cross section how much this is coming. You have this r naught is this is diameter given. So anyhow, you can find out the radius and then calculate. So tell me how much the percentage is coming for circular cross section.
43.75%.
43.75%.
Percent.
So if circular is having this much increase, this much percentage increase in this, basically this is your percentage of cold working. You can think it up as, है ना? Whatever changing in area is happening, that is basically that much amount of cold work you are doing. Now for rectangular one, for rectangular one,
31.43.
great, 51.43%. So what can we infer from here? Your circular cross section is
Circular,
having this.
circular is more harder.
Right. Circular cross section is much harder. Understood?
Yes.
Not much difficult, right?
Yes.
So we'll move to the next question. So you have some. plot given for yield strength versus this grain dia to the per minus hub for brush metal. Determine We need to determine the value of sigma naught and ky from this Hall patch equation. So we have this Hall patch equation as sigma y equal to sigma naught plus ky d to the power minus half, and the values are provided here. And then you need to predict the yield strength of the material when you have this average grain dia. So for the next case, you will have this average grain dia as provided, and we need to find out sigma y. So somehow you need to initially find out the sigma naught value and ky value. So what kind of equation is this? This is linear
Straight,
quadratic.
straight line equation.
So this is straight line,
Linear.
right? So if you think of this y equal to mx plus c, so m can be think of this ky value, the slope of this line,
Yes,
है ना? So basically we will find out the slope of the this straight line initially. So m equal to delta y by delta x, right? Now for this, let's say this is your value d to the power minus half, which is 4 mm. So for 4 of value, you have this yield strength as how much? 175. Sorry. 75, correct? And let's say you have this 8 or take 12 Anyone? Let's say take 12 value. How much this is coming? 175. Or else you can take also 8 one. This will come similar. So tell me how much the slope is coming. That will be your ky value.
12.5.
12.5 megapascal. What will be the unit? Megapascal ky into d to the power minus half. So this will be in millimeter to the power half. है ना? Now if you have this ky value, and then how can you find out this sigma naught value? We simply use this ky value in this equation. So let's say your sigma y is 75. I don't know the value of sigma naught, plus ky is 12.5, that into 4 to the power minus half. Oh, sorry, this is 4 only. D to the power minus half value is 4. Got it? So we got the sigma naught value also. So you got the sigma naught value, you got the ky value. Then you need to predict it for 0.001 How much will it come?
420.28.
420 point.
28.
Okay, got the concept? How we
Yes.
are approaching? Okay. Okay. So this is some question from critically resolved shear stress. So before going into this critically resolved shear stress, mm, yeah, we did some discussion on this slip and twinning. Can you tell me some differences between slip and twinning? Okay, let it be. You can go through any kind of theory book. Now, in critical resolve shear stress, so basically it happens like if you see the deformed any kind of deformed product, no. So on the surface of a deformed specimen, you can see these parallel lines, kind of parallel lines, and basically you can think it of this as slip lines. You know? So those slip lines basically indicate these what you can tell it as this shearing of these atomic planes within crystal with respect to one another, right? So whenever you have this slip, you are having this shearing of atomic planes with respect to one another. Correct. Now, these sleeps are basically resulting in this surface step. So, if you have this kind of cylindrical object, you can see these kind of stretch marks over there, which are basically the slip lines. And slip planes are basically kind of closed packed planes in the crystal, the direction along which the slip occurs, right? So slip occurs along slip direction and across slip plane. So this slip plane and slip direction, these all together is called what? Slip system. है ना? Now the stress at which this slip starts in crystal, that depends on this relative orientation of this stress axis with respect to this slip plane and direction. Are you getting it?
Yes.
है ना? So let us try to understand what happens. Means how can you find out this critically resolved shear stress? Then it will be easy to answer this question. So let us say you have this object over here like this, and let's say your slip plane is like this. If you are having this slip plane is like this is your slip direction, and this is the applied force direction. Correct. This is your applied force direction. F is equal to sigma into A. So this area is your A, this area, right? Now let's say this is my direction, which is normal to this slip direction. So let's say this is slip normal. Now, how can you find out this critically resolved shear stress along the slip direction. So if you want to find out this tower, which is critically resolved shear stress, this if this is a if, and let's say, let me take another color. So let's say this is your angle lambda, and let's say this is your angle phi. Now how can you find out? So across this direction, this will be f cos lambda, है ना? And what will be this plane? Then if this is your a plane, what will be this plane? If you do some simple trigonometry, this plane will be, you will find out as a by cos phi. So this is coming as f by a cos lambda cos phi. Now can you tell me that which value will be giving this highest value of critical resolved shear stress? Obviously you knew this equation anyhow. I explained and derived the equation, and then you tell me that which one will provide the highest value of critical resolved shear stress. So this angle is some 45 degree. This is of course 0. This is something, how much this will be? Less than 45, है ना? And this is greater than 45. I'm talking about this with horizontal. So if you think of this cos value, which angle gives you the highest value? So tower will be the highest, where this cos lambda cos phi will be highest. If you are having same force, same area, है ना? Are you getting it?
The first 45 degree will be
Exactly.
highest.
So cos 45 degree will be giving you the highest value. So whenever this angle will be 45 degree, that time this tower will be highest. Correct?
Yes, sir.
Okay. So similar type of question, but kind of numerical. This was conceptual, the earlier one. So here you have this tensile stress applied along, you have this direction 2 minus 3 1. So basically if you think it of this, so this direction is provided as 2 minus 3 1. Then if normal to the slip plane occurs on a 1 minus, okay, so normal is provided 1 minus 1 minus 1, and then your slip direction is also provided. This is 0 minus 1 minus 1. All the directions are provided, and then it is told that initiated at an applied tensile stress of 3.1 megapascal. So your sigma value is provided as 3.1 megapascal, and then you need to find out this resolved shear stress. So you have this tower equal to, this value is given 3.1 into, I don't know the, I don't know this angles. So you need to find out cos lambda cos phi value basically. How can you find out this cos lambda cos phi value? All the directions are given. Simply do the dot product, है ना? A dot B is AB cos theta. So one vector is given as 2 minus 3 1. That dot 0 minus 1 1. So this will be your cos lambda value. Cos phi will be 2 minus 3 1. That dot 1 minus 1 minus 1. Are you familiar with this, right? I'm not telling anything new.
Yes.
Yeah. Okay. So tell me this cos lambda and cos phi values. So this is some 2 into 0, that plus minus 3 into minus 1, that plus 1 into 1, that divided by root over of 4 plus 9 plus 1, that into 0 plus 1 plus 1. That's how we calculate, right, the dot product. And then for this 2 into 1, that plus minus 3 into minus 1, that plus 1 into minus 1. And then you have this root over 14, that into 1 plus 1 plus 1 root 3. Okay, how much this is coming?
Lambda is 40.88 meters.
You're telling the cos lambda value or lambda value?
Lambda.
Lambda.
Yes.
How much?
40.88.
40.88 degree. And 5.
I will 51.9.
Is this? Actually, yeah, somewhere these directions I have, these are some random values I have provided. These are not correct. So if you think it as this lambda plus 5 should have come this 90-degree, right? These two, because this is the normal direction. Anyhow, so these directions what I have provided, these are not correct. These are some random values I have provided. Uh, Let us take this as fine, any no issue. If this lambda value is coming as this and phi value is coming as this, then you can find out this tower value from here. got it what I'm saying?
Yes, like it's not necessary. You have drawn the all three vectors in the same plane. They may not be in the same plane.
Sorry, come again.
You have drawn the three vectors in the same plane. Yes,
Uh-huh.
but it's not the case every time. The three vectors can be in
Yes,
different planes.
yes, 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 yes. Right, right. Good. Yeah, correct. Okay. So how much these values coming us now? This resolved shear stress.
1.446.
This one, right?
Yes.
Okay. Now again, this is some normal basic question. So it says that a tensile test performed on a metal specimen, and it is found that that true plastic strain epsilon value is given 0.25, and that is produced when a true stress value is given 600 megapascal. And then for the same metal, the value of strain handling coefficient is provided. So K is provided. And then you need to calculate true strain that results from the application of a true stress sigma 2 is 800. So let's say these are one values. This simple means sigma 1 equal to K into epsilon 1 whole to the power n, and sigma 2 equal to K into epsilon 2 whole to the power n. So from here you get the value of n and put it here. K value is same. Okay. Any answer? Should I wait for the answer or we can move to the next question?
0.67.
Sorry?
0.67.
0.67. 0.67. This is value of true strain.
Strain.
Okay. And how much this n value is coming as?
0.29.
0.29. And k value is known. Yeah. Okay. So this is something from this GP zone. Now in GP zone, what happens? So basically, if you see, this is the precipitation hardening thing. Now in precipitation hardening, many alloy system can be strengthened by precipitation hardening mechanism. So basically, there are some mechanism which is called solution treating. One is called solution, and then you are doing quenching. No? Now, in such alloy systems, if you see, always this second phase is in solid solution at elevated temperature, but it always precipitates during quenching. Whatever the second phase is, no? Whatever the second phase is, it always soluble in solid solution at elevated temperature. And then when you quench it and aging at a lower temperature, this comes up ends up with some precipitate formation. Now what happens in GP zone? So in GP zone is grain refinement with decreasing temperature. No. Yeah, this is the fine scale metallurgical phenomena involving this early stage precipitation. है ना? So if you think of this aluminum copper alloys, this is this typical example of this precipitation hardening material. And should I explain the theoretical thing? You have gone through the theoretical part now. So in GP
Yes.
zone, if you, है ना? So if this is your aging time, uh, let me draw this in some brief manner. And then if you have this hardness value, then you have this kind of profile over there. So this is your GP zone where this early precipitate formation will be there, and then this theta dash precipitates over here, and here this you have this theta precipitate, which is the L2Cu. है so the maximum hardness occurs when this amount of this theta double dot theta double prime, or this you can tell it as GP2, is at maximum. here, right? And as prime, theta prime grows in size and increases in amount, the coherent strength decreases. So whenever it grows in size and increases in amount, coherent strain decreases and alloy becomes overaged. So these you have come across. So I'm not emphasizing again and again the things. Okay. So we'll move to the last question then. So it says that for a cold work copper crystal, you have this dislocation density as 3 into 10 to the minus 14 per meter square, and then shear stress required to move this dislocation is provided 150 meganewton per meter square. And you have this base shear stress value is also provided 1 meganewton per meter square. You need to find out the stress required to move the dislocation if the dislocation density is this. So you know this equation, है ना? Rho is dislocation density, tau naught is base shear stress, tau is your shear stress, and then you have this rho 1 value as 3 into 10 to the minus 14 per meter square. Tau 1 is given as 150 meganewton per meter square. Sorry, tau naught is given as 1 meganewton per meter square. You need to find out tau 2 if rho 2 is given as 2 into 10 to the minus 12 per meter square. Can you tell me a quick answer? So basically from here, for all the suffix of 1, you need to find out the value of a, है ना? 150 is equal to 1 in 1 plus a into root 3 into 10 to the minus 14. How much a is coming? Uh-huh.
860,
Huh?
860.5.
How much?
860.25.
850, right?
60, 86.
860.
Yes, 860.25
Okay, 860.5. What is the unit?
meganewton per meter cube.
Now, what will be the tau 2 value? 1 plus 860.5, that root over 2 into 10 to the minus 12. What is the value coming?
Coming very close to 1.001.
Is it
Yes,
1.001? So it's okay. So this is very less, no? This is coming very less. Anyhow, okay. So this was my last question. So yeah, any confusion, anything? How about the numericals? Is it too difficult to understand, or there is some concept to absorb? So for
somewhat.
few numericals, I've tried to make it not that straightforward. Yeah, there is some tricks which you need to crack basically. Are the numericals understandable?
Yes,
है ना? Okay. So if there is no question, we'll finish it here.
yes, sir.
Okay then. Bye bye. Have a good day.
Thank you.